to all of you. First, I have to thank him for being so kind to deliver this talk without any previous consultation. Just yesterday we realized that he was going to deliver a very nice talk in Cambridge tomorrow
evening.
And we said, well, could we get advantage that you are here in our scientific advisory body with other distinguished colleagues here who are advising the ISE today. And he was so kind to say, yes, I'm happy to give this talk for the benefit of all your students, postdocs, and staff, and engineers. So many thanks. Let me briefly summarize a brief 4 pages summary of the curriculum. But it's at least I will make a few notes on Professor Malcolm Longir. I think among the most relevant astronomers in the UK, clearly with a very distinguished career. He has been director of the Royal Observatory in Edinburgh. He has been head of the physics department of the University of Cambridge. He has a very long list of positions in his career. He has been a visiting professor in a long list of centers, from the California Institute of Technology to the European Space Space Telescope Science Institute, to MPI and other institutes in the world. He has honors. He has been just the most recent one, honorary Doctor of Science by the University of Edinburgh. But many other honorary professorships, like in the University College of London, or the honorary member of the American Astronomical Association. I think you are one of the few members in the review, advisory body for the National Science Foundations for the Astronomy Program, non-US member. He has been advisory in many committees, and in particular, he has served at the PPARC, so the old Council for Research for Science and Technology in the UK, as he has chaired tens of advisory bodies and committees. And I will just conclude saying that he is also author of more than 20 books that I strongly recommend you to read, because they are really beautiful pieces of divulgation of science and also scientific physics. So today we are very happy to have you here. Please tell us about it.
I'll tell you about it. That's good. Thank you very much. That's very kind, Raphael. Let me explain. Tomorrow evening, I'm going to give this celebratory lecture, a public lecture for the Year of Light, and also to celebrate the 150th anniversary of Maxwell's great paper on electromagnetism. And this lecture is very simple, except for 2 slides. Okay, but you will enjoy these as well. So this is a very simple lecture, but there are some things in this which many people do not know. So I hope you will enjoy this birthday present, let me put it that, for the equations and for that. I should say that tomorrow evening I'm doing 8 experiments live. Right. You are crazy if you do 1 experiment live in a lecture. You are completely crazy and totally nuts if you do 8. Anyway, it's great fun trying to do this, and it communicates things that you cannot do otherwise. So what I'm going to do is on this list here: light and color from Snell to Young, Maxwell and color phenomena, Maxwell the quantitative theory, and then light is electromagnetic radiation. And then we'll go on quickly to see how things then broke down from that point on. Now, here is something everyone is happy with, Snell's law, telling us how it is that light is refracted through surfaces. I think many people know this. There's a very well-known law there about how matters are refracted between 2 media. And that's in 1621. That is quite early in the whole story. Amazingly, almost immediately, René Descartes applied that idea to understand how rainbows form. And what he realized was, if you've got a sphere of water drop, and there's 1 internal reflection, then there's a minimum angle of deflection of 42 degrees going through this spherical water drop. If you have 2 internal reflections, then it comes in this way round, and there's a minimum angle of deflection, 51 degrees. And this was written up very soon after the discovery of Snell's law in his theory of rainbows. And this is from his book Les Météores of 1637, showing the gentleman scientist. And there you can see the little drop there. This is the smaller angle. And then here at the bigger angle, and you will see inside the drops drawn exactly the light paths through the drops. But notice there is no color. Now this is where Isaac Newton comes in, because in age 22, 65 to 66, any young people in the audience will have to get going, because at age 20 he discovered the binomial theorem, integral and differential calculus, the theory of color in optics, unification of electromechanics, and the theory of gravity. Not bad! Not bad! Now, among the things which he did in this was the famous experimentum crucis. Now, this is the drawing from Newton's writings in 1665, and here is a small hole in the window. It comes through a lens, goes through one prism, and then he's got these holes where you can send the bits of light through a second prism and then see what happens on the screen. This is the experimentum crucis, and there's the schematic diagram of it, and here is the conclusion that light itself is a heterogeneous mixture of differently refrangible, we would now say refractable rays. Now this will be the first experiment that I do in this, just repeating Isaac Newton's experimentum crucis. A nice light source goes through one prism, through a slit, and then through another. Since I could not bring my 6 crates of experiments with me, I have got a little video just as backup in case everything collapses. Now, here you'll see me with the prism. It's slightly burned out there, but this is just to convince you. Now I put the next prism on, and you see it extracts this bit of the spectrum, refracts it through there. And now I try to put in the little slit. This gets very, very faint. I've got a bigger slit for tomorrow night. Here I push this across, I push it across, and then just visible no more is there. Can you see it just no more? There's the red light. If lights were out, you would see there's only right. This is the experimental crucis. I've got it optimized for tomorrow night, so it will be my turn. But that is the essence of the experimental crucis. I don't think many people actually do it nowadays. They just assume it. That's how it works. Now, what one could then do is to apply this idea of the different refractive indices to the droplets. This is a rather nice picture here showing white light coming in here and then getting refracted inside the sphere. And you will see that the red, which has got the least reflection, is going to give the colors of the rainbow. And then inside, all the colors will mix up, so you'll get greater white intensity inside the rainbow. Now, of course, here's my second experiment that I'll do tomorrow night, where I've got a large raindrop, and there it is there, right? It's the bottom of a spherical flask. I've got my light source here. It comes through there, and then exactly the same phenomenon happens for tiny little raindrops and great big macroscopic raindrops. And when I do this, this is what you see, right? And it shows you could actually, the big raindrop does rather well. Look around the edge. Beautiful, all the colors of the spectrum, and the increased intensity on the inside because of the overlapping of all the colors adding up. Here, oops, sorry, I hit the wrong one. Silencio. Good, right. Does that mean I... Right, now... can I get rid of that? Well... Is there something I hit to get rid of? I don't want it to be silence through the whole of the lecture. Let me just go on to the next one. There we get on volume instead. Right, okay. That's right. Okay. Well, anyway, that is demonstrated, and that one will be done live tomorrow night. Now, the interesting thing is, well, there we are. Of course, we're all familiar with the double rainbows very well, but this was then fully understood by Newton. Now, the next thing you can do is to look at another lovely example, which is refraction through hexagons. And the reason for that is that hexagons are formed in the atmosphere. So what I've got here as half of a hexagon, and I'm going to put a laser beam through it, and you will see what happens. So if we do this, all I'm going to do is to rotate that table there. And here you see it goes. And I start rotating it like this. Watch the spot. Right? And I can continue rotating just in the one direction. And what you see is happening is exactly what happens in the case of the raindrops, but now going through the hexagons. That there's a minimum angle of deflection, but now it's only 22 degrees, rather than the other figures that we gave. And that is the origin of what happens in the upper atmosphere. If you go up through the atmosphere, you'll find that all sorts of different structures form at different temperatures and different supersaturations. So we've got these plates like these hexagonal plates and hexagonal columns and so forth. And it's basically these sorts of things which produce many absolutely wonderful effects, such as these. All right? Now, in the Canary Islands, you don't see many of these. But if you are in the far north above the Arctic Circle, you see these very regularly. This is at 22 degrees, that's 22 degrees, and these are the things called sun dogs and all of these types of things, which are absolutely fabulous phenomena. I've only seen them once or twice because even Cambridge is not quite. I've seen it once in Cambridge. But you can go on. This is a wonderful study how all of these beautiful things happen, and even you get things like that. And that to me is utterly staggering. Here's what we see, the 22 degrees, and then here are inverted rainbows. You can see these lines. So it's a good student project. Explain all of this. How does it all come about? There is more. Now, one other interesting thing, if you look back at the works of Newton, and this is taken from Newton's original diagram, this explains why there are said to be 7 colors in the rainbow, right? And it's all related to the idea of harmonic proportion, in that there are 7 independent notes in the just scale. All the ratios are small numbers. And so Newton has got here do, re, mi, fa, sol, la, ti, right? And then, well, therefore, there must be 7 colors opposite them. And that's where this indigo that everyone has great trouble with comes from. You had to put 7 colors in the spectrum to make it all work. So that's it. My wife and I have done a whole pile of other work on harmonic proportions in architecture and so forth. Now, the next bit of the story is Thomas Young. In his great paper of 1801, he discussed how the eye would perceive lights of different wavelengths and colors. And in his picture, the eye consisted of a number of resonators which were excited by the incoming waves. But he realized there's a big problem with that theory. And here are his own words. As it is almost impossible to conceive each sensitive point of the retina to contain an infinite number of particles, each capable of vibrating in perfect unison with every possible undulation, it becomes necessary to suppose the number limited. For instance, to the 3 principal colors of red, yellow, and blue. And that each of the particles is capable of being put in motion more or less forcibly by undulations differing less or more from perfect unison. Each sensitive filament of the nerve may consist of 3 portions, 1 for each principal color. This is the first mention of the tricolor theory of vision. Now notice in what he is saying, he took the principal colors to be red, yellow, and blue. There was no distinction between the mixing of lights and the mixing of pigments, and the theory was qualitative rather than quantitative. Now, this is where Maxwell comes in and starts making quantitative the theory of that. Now, Maxwell, Scottish of course, like me, Scotland's greatest physicist, no question about that. Very good. He was brought up. He came from the landed gentry. He was high-born, and his family were judges. But his cousin was Jemima Wedderburn, She was 8 years older than James, but she's a brilliant artist, and she drew pictures of everyday life in the Maxwell family all the time. And so this is her picture of James and Jemima tubbing. They take washing tubs and they put them in the pond, and they use them as boats. Right? And so here's another picture. They made lithographs of them. And here's James again. And the extraordinary thing is the likeness of this to actual photographs of James. Absolutely stunning. She's a fantastic artist. So this is the tutor trying to get James to come ashore. Now, he was very, very inquisitive from his very earliest times, and he would say, "Show me how it does. I can speak the language. You say, show me how it does." Right? And then he would say, "What's the go of that? What's the go of that? Right? How does it work?" And if he didn't get a good answer, he would say, "But what's the particular go of that?" Now, Campbell will understand the language as well. So, it's a great character. Now, James and Jemima and the father, John Maxwell, they were very interested in the scientific toys that were going on. Now, this is a picture of James again. Notice the resemblance, playing with Toby, doing various tricks. This is another of Jemima's pictures, where here's James, here's Jemima, there's John Clerk Maxwell, and here's Mrs. Weatherford. So these scientific toys were being produced, and many of them relied upon the persistence of vision, the fact that the response of the eye is only about a 20th of a second, and that's how cinematograph things work. So here's one of the Thaumatrope, which was invented by John Paris, and you put different pictures on either side, and then you have a string which you wind up, and then you pull it back and forward like this, and then the two images overlap, as shown here. This is an extremely bad joke, which I will not read out to you. And then, in 1932, the Phenakistoscope was invented. And this is by the Belgian physicist, Plateau, one of your countrymen, right? He and his sons introduced the Phenakistoscope, and what happens is you rotate the disc about the axis, and then you look through the slots here, and then you will see a moving image. Now, we've got literally 50 or 100 of these in our stores in the laboratory. They're the original ones from Plato and company. But they really are rather fun. Here's one that I made into a little, just to show you what happens. You see, there's the gentleman and the lady dancing. You see, look through it, and it's really rather fun. So they really had great fun designing these and playing with them and doing new things. Then the Zoetrope was invented in 1834 by William Horner, originally called the Daedalum, and now you look through the slits here and you would see then the moving image of the diagrams on the inside. And in fact, these became very popular. You can get this on the web. This is Make Your Own Zoetrope. This is a 1905 supplement of the New York Sunday American and Journal newspaper. So again, I didn't realize I was going to cover all the members of our panel. We're going to be highlighted their nationalities here. And if you do this, you can get these nice little pictures like this. And one gets paid for this. Now, here's a more serious one. That again, Maxwell then later used these to make scientific illustrations, moving illustrations. And this is a picture of a triatomic molecule. William Thomson, Lord Kelvin, believed in continuum mechanics through the ether, and to make atoms, the only stable structures he was working on were frictionless vortices. And you can demonstrate if you've got a vortex ring and there's no friction, they're stable structures. And then you can put three of them together and they will remain stable in this sort of picture as seen through the zoetrope. Right? Now, of course, this all disappeared with it, but it's scientifically very interesting. If you've only got the continuum ether, how do you make atoms and molecules? Think on that one. It's really rather good. So here's Maxwell, aged 24, with his colour top. Now, note the pictures that Jemima made are absolutely spot on. You will recognize him instantly on the pictures down here. Now, he had an absolutely vast store of knowledge, completely unstructured, and he was sent to Trinity College in Cambridge to sort him out intellectually. They did not succeed, thank goodness. But among the things he did was to work on how you can actually quantify the theory of colors. And this is him with his famous color top here. And I'll show you how it works just in a moment. This is age 24, and he was always very, very attracted to this. Here's how it works. You take the three primary colors are made by these discs, and then you put them on top of the top here, and then put the color that you want to create on the inner circle. And then you rotate the top very, very fast, and so all the colors get mixed up, and you can work out exactly how much of each of the primary colors you need to make any color. So he chose the red, green, and blue as the primary colors, and then you can produce diagrams like this, a triangle, in which this point here tells you how much blue, how much green, and how much red you need to put in to be able to create the image that the color you observe. And this is the beginning of the development of the tricolor diagrams. And here is Maxwell's original version of the color triangle, showing how the red here, green and blue. This is the modern version of the same picture, showing how you have to mix the three colors to produce what you see. Now, this was the beginning of a lifelong interest of Maxwell in color. In fact, he keeps all of these things going in parallel: electromagnetism, kinetic theory, color, mathematics, knots, you name it. They're all going on in parallel. The famous story of Maxwell and his wife. He is now in Marshall College in Aberdeen, where he was appointed Professor of Natural Philosophy and was fired after 4 years. Now, the reason was they put together the University of Aberdeen and Marshall College, and so they could only have one Professor of Natural Philosophy. Maxwell had just arrived. Another chap had been there 20 years, was an excellent administrator, was there, so one of them had to go. They lost Maxwell. You know. But this is also part of the time of his great work. This is the painting that we've got in the Cavendish, and this is a photograph of Maxwell with his wife. And they've always got dogs, and they're always called Toby. Always called Toby. And in fact, when Maxwell came to the Cavendish in 1871, he would go around the laboratories every day seeing what the students were up to, accompanied by Toby. Toby, I'm sure you wouldn't allow this in your clean room, but things were different in those days. And anyway, the other thing which I love about this picture is, you know about the statement about people growing to look like they're animals. Well, you see, I look at that. Now, it seems it must be true. Now, amazingly, there's been no monument to Maxwell in Edinburgh until a few years ago, when a number of us actually got together and raised £200,000, and there's now this statue in George Street in Edinburgh. There's Sandy Stoddart with his one, and notice there is the colour wheel. Even in his old age, he's using his colour wheel. And Toby. Now, my contribution to this was to insist there must be Toby. Right. So they agreed that they would put Toby, and he loved this, because then he became philosophical about the interaction, interspecies communication. Anyway, that's not my job, but that's you'll see in George Street next time you're in Edinburgh. Do look at the lovely statue of Maxwell. Now, he wasn't yet fully satisfied he got accurate enough measurements of the colors. And this is where he produced this beautiful piece of apparatus built by Smith and Ramage in Aberdeen, his famous light box. And this is to get much more accurate estimates of how much of each color you needed. And it's one of these typically clever Maxwell inventions. Let's just run the machine backwards, first of all. So this is where the eye is going to look at the colors. But now we put white light through here, goes through these prisms, which will split it up into these various colors, as usual. And then what you do is now, if you let sunlight come in this edge and then put holes there, then only blue will come to this point on reflection, only green will come to this point by reflection, and so forth. It's just doing the same thing backwards. And then what he did, I'll just show you what this is now running it backwards. Only the green, the blue part of the solar light will come that way. Green part there, but they will come and then be combined at the output. And this is from the original paper of the theory of compound colors. This is published in the Philosophical Transactions of the Royal Society. And here is how he then had accurate measurements of how much of each of the lights, because he could measure how wide open the slits were, and that gave him an absolutely accurate quantitative estimate of how much light was needed. And that's then where the modern CIE diagrams come from. So I think we're all familiar with these nowadays. Now he also produced the first colored photograph. You know, the more you read about Maxwell, the more you realize he's absolutely the power of Einstein and Newton. There's no, in my biased view, there's no question about this. But I think you will agree. Now what he did then was to take this small piece of tartan ribbon, but now photographed it through 3 filters in the red, green, and blue ultraviolet filter, and took photographs of them. The filters themselves were actually fluid. He just had vessels where you could actually put the colored water in there, and that acted as the filter to do that. And then you had 3 projectors, produced the negatives back through there, added them together, and then for the first time in history, you had 3-color reproduction. Right? He reconstructed this live in the Royal Institution in London in 1861. And these are the first fully colored images ever projected. But he was also extremely lucky. And as you know, in research, you have to be lucky, because his emulsions had no response in the red filter. So how did it work? Now, the answer was there was an ultraviolet leak in the red filter, which transmitted light in that waveband, and then the red dye in the ribbon reflected the UV light, right? And so you actually compensated for the lack of it by the fact you were actually using UV instead of... It's an amazing stuff. So when it was projected, then you got the correct gamma balance. And this is a recent... We've got the original slides in the Cavendish, and Peter Reed took copies of these and then reproduced. This is the best he could do by adding together the 3 separate slides. So all of this are led eventually to the understanding of the rods and cones in the eye, that the rods are very sensitive and can register the arrival of individual photons of light, but they've got no color discrimination. Whereas the cones are less sensitive, but are sensitive to light centered in the red, green, and blue wavelengths. And that, again, is the modern theory of color vision. And here is, again, how that works. These are the response curves, the absorption curves for pigments in the cone cells. So normal trichromaticity, which is what we've been talking about, that's in normal human vision, old world monkeys, and apes. All right. They've all got tricolor vision with these. There's anomalous trichromaticity, which is in 6% of human males. Women don't have this. It's only the men that are really seriously colorblind. And what's happening here is that you can see that there's not the red response. There's some discrimination. But then dichromacy, that's for non-primate animals, and 2% of human males who've got no red response at all. So maybe among this audience there might be one person who's colorblind. I won't embarrass you by asking you to raise your hand, but statistically, you're there. Now, of course, what we actually see is determined by lots of other factors. For example, the surface smoothness or roughness, highly reflective or polarizing, and so forth. And all of these contributed to the color experience you get. But there's another interesting effect that the blue cones are very sparsely distributed on the retina. And that can fool the eye if the object is observed at low enough resolution. You will see things that you ought not to. The brain, as you know, does an enormous amount of image processing. And I'll show you one of my favorite examples, which I hope will work for you. So what I'm going to do is, here's a yellow sheet and a white sheet. And I will bring up this wiggly line and just put it right across the interface between the two. Right. Now, you can see, again, the wiggly line, and you can see the yellow and white quite clearly. Now, I'm going to move it further and further away and see what happens. This is just taking the same one now, and I'm going to just move it further and further away. Now, you may have seen the yellow begins to leak into the white area, and the white leaks into the yellow area. Shall I do that again? Now, it doesn't happen, it doesn't work for everyone. It depends how good your eyesight is. But if you look, just watch what's happening. And that's entirely because of the different distribution of the cones on the back of the eye. So you know that that's not happening, but the brain interprets it because of the distribution. So this is why color in art and everything else is a very slippery subject. Although we can do Maxwell-type experiments, there's many, many other things which interpret what we see. Now, Thomas Young, in the same great paper of 1801, also came up with the wave theory of light and put it on a firm physical basis. Now, he was an undergraduate at Emmanuel College in Cambridge, and the story goes that he came to this idea by looking at the pond in the paddock at Emmanuel College. And this is a photograph of the pond in Emmanuel College, and you can see interference of waves. Right? I don't know who took this picture. It's a jolly good picture. There you see the waves on the paddock interfering. And so he had the idea that that was how it worked. And in particular, he carried out the famous double slit experiment, which showed that you got this interference pattern like this, which you're all familiar with, the double slit experiment here, two slits here. Then when the waves interfere, it's coming from a single source here, then you get this very characteristic diffraction pattern. You're all very familiar with that. Now, of course, you can guess I'm going to have fun with this in the lecture, because we will actually just show how it works. This is, again, the wave theory of light, according to Young. But what sort of waves are they? You know, what are the waves that the light is consistent of? We're going to get the answer later from Guess Who. So again, this is the sort of experiment I'll do tomorrow evening. It's very simple to do nowadays. You just get a laser and then get lots of these little slits to see what happens. I'll just take this row. Again, this will not surprise any of you. If you've got a single slit, we know you get this characteristic diffraction pattern. If you've got lots of slits, then you get the same diffraction pattern, but now you get all the maxima in it. And then if you've got fat slots, you've got a different distribution of the spots on the screen. If you've got the letter H, you will get this pattern with both the horizontal and the vertical interference fringes. And if you've got lots of holes, you'll get something like this, right? But of course, in this case, I've done it again. But in this case, you can see that they aren't holes, they're diamonds, all right? The tiny little holes are diamonds, and you can infer that from the fact that they're across in this direction. And I use this as an illustration just to say, look, this is the beginning of the use of interferometry as the way of doing so many different things that we take for granted nowadays. So, of course, I have to put in the example of the great Michelson interferometer here. Here it is here. This is on the 100-inch telescope. but also it leads to optical interferometry, and also to the discovery of the DNA molecule, which is using exactly the same techniques of interferometry, but now with X-rays, and now we do it with electron diffraction, and so on. So, now, of course, what I then tell everyone, but of course, this is intensity interferometry. Where's the phase? Because the phase always tells you where you are on the image, and I say, that's a clever thing to do. But again, as you all know, there are ways of recovering the phase by various tricks. The radio astronomers just go and measure the phase, and that's great. Reconstruct it. But in the case of X-rays, you've got to do tricks like replacing some of the atoms so you get differential. And that's not the point. The point is the idea of interference of waves lies at the bottom of so many scientific disciplines nowadays. Now, let's go back to Maxwell again. Because, again, as you know, Maxwell discovered his equations. I want to show you exactly how he did it. You may find this amazing. I find it amazing. But it's all true. Okay. So here's what he did. Now, you were able to get rid of silencio. We need to get rid of silencio. Perfect. Now, I think Maxwell was not only a great theorist, he was a great experimenter, as you've seen already. But when he began to tackle the problems of electromagnetism, what he said before... It's my big thumb. That's good. Sorry, my apologies. Before I began the study of electricity, I resolved to read no mathematics on the subject till I first read through Faraday's experimental researches on electricity. That's what he writes in the foreword to his great treatise on electromagnetism, which appeared very much later. Now, let's see how he built up what we now call Maxwell's equations. Now, he started by working with analogy. Now, analogy from Maxwell was paramount way of doing things. You understand something, and then you use the analog to understand something else. And that was the basis of his way of thinking. So in this case, he said, I'm going to take Faraday's lines of force really seriously, right? Until then, in Faraday's work, there's not one equation. He was totally mathematically illiterate. He was just a totally brilliant experimenter. But he invented the concept of lines of force for being able to evaluate the effects of magnetic fields. So what Maxwell did was start by looking at the analogy between the magnetic flux density of a bar magnet and the flow of a fluid. And if you think about it, if you're in free space, the divergence of B and the divergence of V are both zero. Right? So it all works rather well. Now, to cut a long story short, putting together everything that was known in 1856, he had got in modern notation this far. Curl E equals dB by dt, curl H equals J, div, what we now call D equals rho E, and div B equals 0. But his worry was he had no mechanical model for what was going on. Right? And in Maxwell's thinking, he was always basically thinking in Newtonian mechanical terms rather than what he was going to, his great revolution that he was going to make. Now, in 1845, Faraday discovered Faraday rotation, which was very important, the rotation of the plane of polarization when you've got a magnetic field going in this direction. And so Maxwell inferred that magnetic fields were essentially rotational in nature. There was a rotational, which fitted rather well with the fluid analogies. So, what he did was, we will now represent a field line by a rotating vortex tube. Right? And then, to get a magnetic field through all space, you simply fill up the whole space with these vortex tubes. Right? Now, I'm not joking. This is actually in the papers. So, what he's doing is putting together, to get the field lines, you put together lots of them like that, and that's your model, your mechanical model for the magnetic field. Now, there's only one problem. You can see that if you've got these rotating vortices, then friction here will cause them to disrupt. And so he used a mechanical solution. You put ball bearings or idle wheels between the vortices, and then they can all rotate in the same direction, and you've solved the problem. So you've got a mechanical model with these idle wheels in this distribution. And amazingly, I do this in my book on theoretical concepts in physics, you can actually explain all the known electromagnetic phenomena at that time in terms of this model. You can get induction, you can get all of these things can be explained on this model. And this is the picture from Maxwell's paper published in the Philosophical Magazine, and now he's represented these tubes by hexagons. There they are there, and there are the idle fields between them, rotating in the opposite direction to the rest. So I'm not joking. This is what is in the paper. Right? So he then realized that if the little idle fields were free to move, then you had a conductor. If they were not free to move, you have an insulator. But if you apply an electric field to them, then they'll get displaced. Right? And therefore, in principle, you can see how rapidly that disturbance moves through the structure of the rotating tubes and the idle fields. Right? So what he said is, we've got to add in the effect of that displacement of little particles into the equations we've got already. And so what he did was then to add these terms here, which depend upon the displacement, and this is the origin of the displacement current. It's because you're displacing the idle fields a little bit under the influence of the electric field. Once you do that, then you then solve the equations very straightforwardly and found, to his amazement, the speed at which disturbances move through the medium is just the speed of light. It was utterly astounding, because there was a recent very high precision value from Foucault, and also Weber and Kohlrausch had measured the ratio of electrostatic to electromagnetic units with very high accuracy, which is what you need to be able to put the right constants into the solution of the equations. And again, that came out within 2% of the speed of light. It's utterly amazing stuff. And here's his word. We can scarcely avoid the inference that light consists in the transverse modulations of the same medium, which is the cause of electric and magnetic phenomena. And that is the first, this is the first presentation of this great discovery. Now, he realized that people might be a little bit skeptical about vortices and idle fields in the vacuum, because this is a vacuum we're talking about. Right? And so he said, I do not bring it forward as a modal connection existing in nature. It is, however, a conceivable modal connection, which is mechanically conceivable, and it serves to bring out the actual mechanical connections between known electromagnetic phenomena. And notice the word mechanical continually appearing at this stage in the development of the theory. But what he had done, one of the great unifications in physics, he unified light and electromagnetism. For the first time, they were shown to be the same thing, theoretically. Now, Maxwell realized that people might be upset about his mechanical model for the electromagnetic field, and so he then developed the whole theory on a much more abstract basis, without any special assumptions about the nature of the medium through which the magnetic phenomenon propagated. There are no longer any vortices or ideas, only fields. To quote the word of Edmund Whittaker, in this, the architecture of the system was displayed, stripped of the scaffolding by aid of which it had been first erected. Now, there's a double centenary happening this year. It's the 350th anniversary of Philosophical Transactions of the Royal Society, which was founded in Newton's time, and also the 150th anniversary of Maxwell's paper. And so I was on the board which had to select the 15 greatest papers from Philosophical Transactions, and then we gave out these essays to people. So I was asked to do the one about Eddington and the deflection of light by the sun, which I did. And then 2 weeks before Christmas, I got a message from the Royal Society saying, unfortunately, the person who was going to write about Maxwell's equations has gone blind and cannot write the article. Could you write us an article about this paper before Christmas? So there was no way I was not going to get this paper in this edition of the thing. So I dropped everything, and for 3 weeks I absorbed myself totally in the paper. A wonderful experience. But I learned so much from doing this that you will not learn in the books. And I just want to share one or two of the things with you now. Now, one of the problems, if you don't like mathematics, just close your eyes for a moment. It'll all become all right. For the Gore details, it's all been published already, so it's on the web, actually, in the 6th of March. For all the Gore details, say this paper, a paper which I hope to be breakdowns, a commentary on Maxwell. Now, the first thing I did was to take the original 55-page paper and convert it into LaTeX, what any of us would do now. And then having put it into LaTeX, then I changed the notation from Maxwell's notation to modern notation that we would recognize. So, for example, you see we've got electromagnetic momentum, FGH goes to what we now call the vector potential, which is there in the paper. We've got magnetic intensity, alpha, beta, gamma goes to HXI. You see the way, you just got to go through all of this. And then, when you do that, here are Maxwell's 20 equations for 20 variables. Uh-huh. But you can see, that's what people always say. 20 equations for 20 variables. But actually, it's not nearly as much because they've separated each of the components, the X, Y, Z components of many of the things we would now regard as simple vectors. You see there's A, well, that would only be now one vector there. Here's H, that would be one vector. Here's D and E, that would be one vector, and so forth. So of the 6 equations, that gets rid of 12 of the extra equations right away. So anyway, once you've done this translation, there are the 20 variables that you need to determine. You see, it's just what we know. But here now, I've now done one step further and now rewritten these equations in the modern div grad curl notation, and you will see they're actually identical to what we call Maxwell's equations nowadays. There are. These are the 4 that I've got here. Here's B equals curl A. There's curl H, and so forth. You can see we just basically got Maxwell's equations there. Hertz and Heaviside are given the credit for making Maxwell's equations intelligent. If you do a sensible thing, it's right there already. It's all there, including, notice, the V cross B term, which we normally call the Lorentz force. It was there in Maxwell in the 1865 paper. But the really big philosophical change is everything is now written in fields rather than forces. There's not a force in this set of equations. Right? And rather, the forces on particles have to be worked out by mathematical operations on the fields. And we nowadays don't even worry about that, but in terms of the evolution of scientific thought, that was an absolute giant step to throw away the forces. In the process, you're going to throw away the mechanical interpretation of the fields. So Maxwell realized he'd done something pretty good, and there are now the equations in their modern form, and here's what Francis Everett called a rare moment of unveiled exuberance in a letter to his cousin Charles. I have a paper of float containing an electromagnetic theory of light, which, till I am convinced to the contrary, I hold to be great guns. And this is this great 1865 paper. Now, I'll just show you one quote, and this gets to the whole nub of what he actually achieved within the paper. Here it is. In speaking of the energy of the field, however, I wish to be understood literally. All energy is the same as mechanical energy, whether it exists in the form of motion or that of elasticity or in any other form. The energy in electromagnetic phenomena is mechanical energy. The only question is, where does it reside? On the old theories, it resides in the electrified bodies, conducting circuits, and magnets in the form of an unknown quantity called potential energy, or the power of producing certain effects at a distance. He goes on. On our theory, it resides in the electromagnetic field, in the space surrounding electrified magnetic bodies, as well as in those bodies themselves, and is in 2 different forms, which may be described without hypothesis as magnetic polarization and electric polarization, or according to a very polar hypothesis as the motion and the strain of one and the same medium. And the key, these words are so absolutely fundamental, because what he had done is to replace action at distance, which is what all the laws previous had been, gravitation, electromagnetism, electromagnetism. He replaced this by the concept of fields acting throughout space. And in terms of the intellectual leap, it's absolutely colossal. Now, sadly, the proof of the electromagnetic nature of light wasn't fully confirmed until Heinrich Hertz did these brilliant experiments with this type of apparatus 9 years after Maxwell died at the age of 48. So Maxwell never lived to see it. But these experiments of Hertz, using purely electromagnetic phenomena, demonstrate reflection, refraction, polarization, diffraction. All the properties of light are there in the properties of the propagation of electromagnetic signals. Now, here's what Einstein writes about Maxwell. We may say that before Maxwell, physical reality, insofar as it was to represent the processes of nature, was thought of as consisting of material particles whose vibrations consist only in movements governed by partial differential equations. Since Maxwell's time, physical reality has been thought of as represented by continuous fields governed by partial differential equations and not capable of any mechanical interpretation. This change in the conception of reality is the most profound and the most fruitful that physics has experienced since the time of Newton. And the interesting thing is, the point is that Maxwell remained actually to the end much more a mechanical person. But the next generation of physicists, the Einsteins, the Hertzes, and all of these people, Lorentz and everyone else, they grew up with fields as being the primary thing which drives things in the universe. So it really is a fabulous story. Now, one of the great ironies of this story is that these great experiments which proved the correctness of Maxwell's theory also led to its demolition in some sense, right? Because in the same experiments, Hertz discovered that when ultraviolet light is shone on the cathode of a vacuum tube, electrons, what we now call electrons, are ejected. This is the photoelectric effect. And its features cannot be understood in terms of classical physics. Now, what I'm going to do tomorrow night is to do this experiment live in public, showing what happens in the photoelectric effect. You've got a mercury lamp here, and you put it through a prism or grating, and then you've got a photoelectric detector here. Yes. This is just the apparatus that we've got. We've got the mercury vapor lamp, we've got transmission grating, a voltmeter, and we've got a photoelectric detector. And the remarkable result was found is as you decrease the intensity of the radiation hitting the detector, what you find is that the energy of the photoelectrons didn't change. You got the whatever the intensity was, you were still getting the same energy of the ejector. What was going on? That was very difficult to explain in terms of classical terms. Now, Einstein's paper of 1905 on quanta really is an absolutely staggering piece of work. Now, the interesting thing about that, and again, see my book, my book Theoretical Concepts in Physics, where I explain exactly what he did. To get here, it was entirely statistical mechanical, and in a word, going to the V part of the spectrum, you can show that that part of the spectrum statistically is as if particles, individual particles were causing the effects. So he then transferred that idea to say, are these real particles? Yes, they are, and they can cause the photoelectric effect. And what he came up with, I've done something else, but he came up with this famous equation that the energies of the incoming photons depends on the work function, and then the energy with which the photons are ejected, which is just going to be the voltage on the voltmeter at the output stage. Well, I'm able to do this live because there are these 5 lines in the mercury vapor lamp, and you just move the detector across the lines to see what the energies of the photons are. And there it is. There you'll see that we've got here the yellow line, which you can scarcely see, the green line, and then the ultraviolet line scale, and so forth. So yeah, we just do this line, and it's one of these experiments that works every time. Every time you do it, you get the perfect answer. So I recommend it for public demonstration. All right. And here's what you get. You'll get points like this on the graph. These are the voltages that you get from there, and then you just fit it with a straight line, and you get exactly the value of H over E. And of course, that is the whole guts of the photoelectric effect. And this is the version that Millikan produced in 1916. There you see all the points lined beautifully on the straight line. And it's always nice to see what Millikan said about that experiment. The prediction was made in 1905 and was carried out in 1916. And here's what Millikan says. We are confronted, however, by the astonishing situation that these facts were correctly and exactly predicted 9 years ago by a form of quantum theory which has now been generally abandoned. He goes on. He refers to Einstein's bold, not to say reckless, hypothesis of an electromagnetic light corpuscle of energy issue which flies in the face of the thoroughly established facts of interference. Quite right. So there was something funny had gone wrong. Now, I received this new experiment we're going to be doing tomorrow evening just before I came out to the Canadian. I'm going to work absolutely flat out to make sure we get it. This is the quantum double-slit experiment. Right? So now what we're doing is we're going to reduce the light to a very, very low level, do the standard double-slit experiment, so the photons are only arriving at a rate of typically around about, in the case that we've got about 10 per second. Right? Only 10 per second are coming through the double-slit experiment, and so they're coming photons one at a time. Now, I haven't had time to make a video, but what we did manage to get just before I came on the plane to come out here, we got the first count rate of the photons as we move the micrometer slit across here. So we've got a light bulb here, we've got baffles, we've got a single slit here, double slit here, and then because this only costs £5,000, this bit of apparatus, we only get one photo detector at a time. You can't get an array, or else it costs a factor of 100 more. But your technology department might make me one. I would be. So instead, what you do is you just use the micrometer and then move this slit across the diffraction pattern and see what you get. And here's our first experiment, showing that with the photons arriving one at a time, you still get the diffraction pattern, right? And of course, as all the students say, how did they know that? Right, which is the question. Anyway, don't you think that's rather good for our first experiment? There you can see the diffraction pattern. Again, these are the counts in 10-second intervals. So you see, even at maximum, we're only getting 10 photons per second coming into the apparatus. I love this experiment. Well, the best thing to do is just to quote from Richard Feynman's lectures on physics, chapter 37. And they said, we choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot explain the mystery in the sense of explaining how it works. We will tell you how it works. In telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics. And what I love about this experiment, it is showing absolutely the contrast and the similarities between the quantum and the continuum picture of electromagnetic radiation. Now, if you want to understand how it all got reconciled, see my other book called Quantum Concepts in Physics, where I absolutely take apart all the stages by which we got to quantum mechanics as we know it now, and that involved changing the whole way in which we look at how phenomena work at the atomic level. But that's more or less where I'm going to stop with you this morning. I go on and do gravitational bending of light. I've got one of these lovely lenses whose diffraction goes 1/r from the center, and so you can get all the distorted images you see in clusters of galaxies appear. So that will be the end. But for the moment, that's the end. Thank you.
Thank you. Questions?
very struck by the theme of continuity and discontinuity, particularly early on. So on the one hand, you've got the discovery of atoms, and yet they're working like mad to try and come up with a theory of a continuous medium which can exhibit this property. And then on the other hand, you've got light, which is demonstrably continuous, and they're working like mad to try and come up with a theory of it in 3 discrete parts. Why did they do that?
Well, it's a very, very good question. Now, I think what we find it now difficult to do is to transport our thinking back to the 19th century. That's almost the biggest difficulty that we have. But the idea that things might be quantum, although atoms were thought to be following on from the Greeks, and then to Dalton's atomic theory, where you add together atoms to make molecules and all that sort of. That was all in literature by the early 19th century. So the ideas atoms were there, it was all in the literature. And then when you look at Maxwell's statistical mechanics, when he derives the Maxwell distribution, for example, that is all dealing with statistics of individual particles. But again, the idea of particles was a very contentious business all until the late 19th century. By the end of the 19th century, most people had accepted that particles existed. But there were still people who rejected that as being, if you can't see the particles, how do we know that they're there? And the original kinetic theory couldn't explain all the details of the specific heats of gases. So what I mean, they were trying to solve what I would call major problems using classical techniques of particle interactions, collisions, or else continuum mechanics. So that's the frame of mind you've got to get yourself into, and then it begins to make more sense.
Why are they trying to discretize the spectrum of light? Why were they so keen to divide light up into 3 or into 7 or whatever? That's the frame of mind I'd like to understand better.
Well, that takes me back to my lecture about harmonic proportion. Because if you look at the time of Newton, for example, not long after Kepler, Kepler's Harmony of the Worlds, for example, fantastic work, had everything being related to musical harmonies. So that for the perfect operation of the universe, you had to have harmonic numbers, the ratio of small whole numbers, 2 to 1, 2 to 3, 5 to 3, and so forth. And in architecture, the assumption was the perfect room dimensions are always these harmonic ratios. And my wife and I have worked on that one, and showing that there are some cases where it does happen, and others it's random chance, and so forth. But in Kepler's Harmony of the Worlds, which is very influential, everything had to be related to harmonic proportions. So when you look at the colors, Newton said, look, that's probably something you've got. Okay, we know it's all continuous, right? But that was the feeling at the time. One other interesting thing, that Newton's aperture to do the experimental pictures was just too big to see the Fraunhofer lines in the spectrum. If he'd actually used a smaller slit, he would have actually seen the dark bands. That's right. Yeah.
Have you seen the episode of the new series of Cosmos, which is looking at light, which deals with the way in which Fraunhofer interacted with that? Do you know the program I'm referring to?
I don't watch any science programs on television.
Okay, all right. Well,
it's make you unhappy.
It's
to be honest. But I've been through the original works of Fraunhofer in more detail than I would ever wish to.
So where does Fraunhofer's work fit into what you've been explaining?
Oh, that fits in. The key experiments were 1814, and there his motivation was entirely military, as so many of these things are. He was the director of the Benedict Brown glass factory, which was making the best possible glasses for military instruments. So you had the better lenses, better, etc., than would be made elsewhere. But in order to do that, he needed great standards. And so when he put one with very good lenses and subsequent diffraction ratings on the solar spectrum, then he saw this plethora of lines coming in. He then did it on the brightest stars and found them again. But nothing then happened until sexually in the middle of the 19th century when they began to take them seriously as astronomical indicators of the chemical elements. And again, Bunsen and Kirchhoff's great series of papers on the chemical composition of the solar atmosphere is absolutely beyond. So all of that leads in directly into astronomy. But the important thing about that is that the understanding of the spectral lines was then going to be ultimately into the quantum interpretation of the spectrum. So it's a slightly different story from the one I've been telling today.
When you put magnetic sand in the presence of a magnetic field, you sort of visualize the lines, but it is sort of fake because the field is continuous. In which sense this experiment could have influenced the idea of the magnetic field lines or something?
Well, Faraday's invention of the lines of force was entirely stimulated by what happens to iron filings when you put it on a sheet and you put a magnet underneath it. You tap it, as I'm sure you...
But that is fake, no? Because that is, in some sense, it is related to the properties of the sand more than the magnetic field, because the magnetic field is continuous, so there is no reason to have particular lines.
No, and because this is one of the things we must get clear to undergraduates, which is it is simply a model. The number of lines per unit area tells you the strength of the field, and the mean direction tells you the direction of the field. It is simply an artifact. That's all it is. So the magnetic field line of force disappears as soon as you write in terms of the vector notation. So it's simply a vehicle that was used by Maxwell by analogy, because the divergence of the field lines, just like the divergence of the streamlines, will tell you about the flow of water or the strength of the magnetic field. It's simply a device. I had great trouble when I was an undergraduate. I said, look, how can I have one field line per unit year? What the devil is going on? And you've got to be careful how you teach this stuff. It is a visualization, an aid to understanding what's going on.
Hi, just a question on the context. How was the theory received? There were any competitive theories of electromagnetism at that time?
The Maxwell theory.
Yes.
There were. And in particular, people like Weber, Helmholtz, had their own versions, all of which were action at a distance theories. They were not. They had not emphasized the field aspect of the way that and Maxwell's theories were not really totally integrated until the Hertz experiments. And partly this was because if you look at the paper, the mathematics is, for us it's quite straightforward, but it was pretty forbidding if you were not used to dealing with what we now call partial differential equations and the operations that you had to go through. So that was one reason. The other reason is that Maxwell was so modest, and still, in 1870, he reviewed all the theories of electromagnetism when he was president of the physics section of the British Association for the Advancement of Science. And he described all the other theories in his lecture, and he said, there is another theory which I prefer. And didn't even explain what it was, right? And so, as Freeman Dyson writes, what it tells us is that modesty is not always a good property. He should have pushed his ideas a little further.
Let me rephrase. It's at that time of Maxwell's theory that you require an ether to propagate wavelength, or it's before?
That again, I missed the keyword.
So the ether,
yes,
the ether theory. This is actually substantiated with Maxwell theory, which we know is not correct, or it's not, or it was the theory was earlier.
Maxwell was convinced, even when he'd done this paper, that these were phenomena going on in the ether.
Exactly.
So I think you'll find it that, in fact, in the 1878 edition of the Encyclopedia Britannica, Maxwell wrote the entry on ether, right? And it's a brilliant essay explaining exactly why you need to have the ether. This is long after he'd actually published the equations. So he was very much on the ether side. And even more amazingly, his very last posthumously published paper in 1880 has the seeds of the Michelson Michelson-Morley experiment. It was picked up by Michelson from a letter to the United States, who Maxwell was inquiring whether you could measure the orbits of the satellites of Jupiter accurately enough to be able to measure the impact of the speed of light going towards you or away from you. And that then what Maxwell wrote was, this is far too small an effect to be detected. Michelson then did the experiment in 1880, the first crude experiment. He got his sums wrong and got the wrong expected, half the expected difference, time difference, and so he had to redesign the experiment, and then in 1887, Michelson and Morley did their experiment. And the significance of that result is utterly gigantic. It's around about 80 sigma of the null result. You know, I ask our students, work out how significant the Michelson-Morley experiment was. You know, there's no way it could be. So that, but again, that was Maxwell trying to measure the properties of the ether in his almost his very last paper.
Are there more? Yes.
It's a really easy one. What's the gig tomorrow evening?
Huh?
What's the gig tomorrow evening? Where is it?
It's in the Cavendish laboratory in Cambridge.
And is it televised?
No, we may make a recording of it, but
Okay.
I've already got 700 people booked to come to see it, so it'll better go well. Huh? Stomach cancer. His wife was very unwell as well. They were both, but he kept working until about 4 or 5 months before his death, doing all of this stuff. And you know, running up the history of the laboratory, he became the first Cavendish professor of physics in the Cavendish, and he did a fantastic job setting up really a world-leading, state-of-the-art laboratory at its time, and kept on producing papers. That's my next book, which will be published next year. If you're interested,
Are there more questions? No? Okay. Do you want to add anything? No, just let's thank Professor Marco Longair.